Hey, welcome to our final video on exponential models. In this video, I just wanted to talk about a couple of other classic exponential models that typically come up. Um, this year's been interesting because we've motivated quite a bit with COVID and infection models. Typically, the way that college algebra approaches exponential models is through interest rates. So that's what we're going to do through how you earn interest on an investment. Okay, so we're going to talk about a couple different kinds of interest. We'll start with yearly interest. So let's say that you invest a principal P. So you invest P at a yearly interest rate of 7%. So that's what you would expect to see. If you were invested in the stock market across a year, you might expect to go up 7%. Then we're going to say create a model that tells us how much you have after a time n. So after n number of years. And this is actually just like our COVID model, where we're going to have at the start, so year 0, we have an amount P. After 1 year, we have P. So we still have the same amount we invested plus 0.07 P. So that's translating that 7% into a decimal. And so we can factor out the P. We've gained 0.07 times P amount. Year 2, then our investment now on the year 2 is P times 1.07. So that's the amount that we had at the end of year 1 plus 0.07 times P times 1.07 again. So we have the amount that we had at the end of year 1 plus 0.07 times that amount that we had at the end of year 1. And we factor out P times 1.07, that, and we're left with 1 plus 0.07, which is P times 1.07 squared. So that's yearly interest. Yearly interest compounded yearly. Now, what if we have our yearly interest rate of 7%, but we compound monthly? Oh, and I guess to just wrap up the details above, if it wasn't clear, we have the amount that we have at the end of the nth year is P 1.07 to the n. And that's just following the pattern that we've seen, where at the end of the second year, we had P times 1.07 squared. And the end of the first year, we had P times 1.07 to the first power. All right, but now we're going to compound monthly. And the way this works is that now we need to do 12 compounds throughout the year. And so we need to determine our monthly interest rate. So if we have 7% interest rate yearly, then monthly we have 0.07 divided by 12. And we're going to get 12 of those throughout the year, so that adds up to 0.07. And now we do the same computation. So f of, except I guess it changes a little bit. So f of 1 is now equal to the amount we invested times 1 plus 0.07 over 12 to 12 to the n, because we had 12 of these intervals happen. So we end up with 12 times as many. 1 plus 0.07s over 12. Oh, and that n shouldn't be there because we're evaluating f of 1. So it's like that n is 1. Then we get f of 2 is p times 1 plus 0.07 over 12, so our monthly interest rate. And now we've, at the end of 2 years, we would have compounded it 24 times. So we end up with a 24 there. And that 24, just remember that's 12 times 2. And finally, f of n is p of 1 plus 0.07 over 12 times 12 times n. So we're going to do, so this is the number of months, and this is the monthly interest rate. And so that's all there is to it. And actually, we can even talk about things like f to the 1/2 now, because if we plugged in f of 1/2, we would get p to the 1 plus 0.07 over 12, 12 to the 1/2, which is this. And so that 6 is saying that this is after 6 months. So we can actually calculate it by just a fractional number of months. Okay. And now the best thing that we can have is continuously compounded. And that's when it's beyond monthly, beyond weekly, beyond daily. We're getting compounded continuously. It's even better than compounding even every 1 second. And we get that this is going to be f of x is approximately however much we invest times 1 plus our interest rate of k for a giant number k. So now we're thinking that we're compounding in super tiny intervals, really tiny intervals, like millisecond intervals, even smaller than that. So to fill up a whole year, we need a ton of them. Then we have to have k amount of those compounds in that year times then x, which is the amount of time that's passed. And maybe you see where this is headed, because this is just like what we were doing with the COVID model, where we're dividing by a big number k and exponentiating by the same number k. The only change now is we have this 0.07 here. That ends up not being too much of a trouble, and this actually evaluates to p to the e to the 0.07x. So now we don't even have to worry about an interval. This is actually nicer because we don't even have to think about like how often we're compounding it. See that k is completely gone now. Whoa. Sorry about that. I think my Outlook, my OneNote just crashed. So let's see what happened. All right, so we still have most of the pieces there. Okay, so we have, now that this is our model, where we have interest rate, our x is time, and our p is initial amount invested. And that's, this is our model for continuously compounded interest. The details of why the 0.07 come up to that x are a little bit complex. We have to use something called, well, I guess we've already seen limits, but not in terms of end behavior, but we're going to look at the end behavior of what this function is. And it turns out that using some techniques in calculus, which we're obviously avoiding because this isn't calculus, we can show that that 0.07 has to come up to the top. For right now, you'll just have to take that from me on faith. And so let's run through an example. Okay. You invest $1,000 in Tesla stock, and it has average growth of, right now, I think it's doing pretty well. So let's say 11% a year. All right, let's say create a function that models, create a function that models your investment over time. How much will you have after, let's say, 3 years? All right, so this is pretty easy. We're just gonna plug in the pieces into our formula. We have, sometimes we call this A of t, so the amount at time t of PE to the RT. T is our variable, so we don't need to worry about it. P is the amount we're investing. So we know that that's $1,000. Then we have E. We don't have to change anything there. We know what E is. R is 11%, so that's 0.11. And T stays the same. So that's our model. And now we can check how much we have after 3 years by just plugging in 3. All right, and then now we just have to deal with evaluating this. If this is a test, we can just leave it like this and this is fine. For homework, this is a good place to pull out a calculator and we'll find, I'll compute it really quick on Wolfram Alpha, what this value is. All right, so it looks like this is approximately 1.39. I'll do little approximations there. So that gives us $1,398. after 3 years, which isn't a bad investment if you're thinking about the real power here is when we're looking at really long-term investments. So after say 27 years, we have A of 27 is approximately 1,000. Well, I guess I'll do it exactly first, which is 1,000 e to the 0.11 times 27, which is 1,000 e cubed times 0.99, which is approximately 1,000 e cubed. E is a bit less than 3, but it's more than 2.5, so this is maybe 24, maybe about 24. So that would tell you that after 27 years, you're up to $24,000. So really good return on investment. In particular, this is why it's good to save for retirement young, where you can invest like $1,000 right when you get a job. And then after 27 years, so maybe you're 47 at the time, that's already turned into $20,000. And after another 20 years, when you're finally ready to retire, it's maybe gone up to 50 or 60,000. And that's all just from an investment when you were young. So that can be really, really good. All right. And that's it for models. I think there's one more, it's on half-life of chemicals and how those decrease, but I think I'll actually just throw that on homework. All right, see ya.